Hey, everybody. All right. Yeah, I'm Paul Dix. I'm the founder and CTO of InfluxData. We are the makers of InfluxDB. Um, so this talk is quite a bit about Flux, which is a new language that we're building. It started as a query language. It was called previously IFQL. It has since been renamed because of a couple of things. One, it's no longer a query language. And two, it's no longer tied to InfluxDB specifically. So right now, I'm thinking of it more as like a data scripting language. It will be Turing complete. You could write programs in it, but we're scoping it to focus specifically on working with data. It's functional in style. All the code is MIT licensed, and this applies not only to the language itself, so the spec is out there, it's open source, it's public, but also the runtime and the engine that we're building, all written in Go. So as most of you are probably Prometheus users, I thought, your question would be, so what? I don't really care. This has nothing to do with me. And when I first proposed this talk, there were a couple of things that I thought might be interesting to this crowd. One was I was thinking about high availability, right? If you could query multiple Prometheus servers in one engine, you could engineer some sort of high availability thing that would be kind of cool. And the thing is, as I started writing code for this, I was like, okay, there are far easier ways to create a high availability Prometheus setup that hits your requirements than this. So I kind of scrapped that. And then I thought, okay, well, what about sharded data? You have separate Prometheus servers running in different data centers, and you could use this engine to combine that data. And then I thought, well, actually, and this is my intuition, I don't know if this is actually true, but my thought was, for most people that have sharded data with Prometheus, they actually combine the data in Grafana, right? They have multiple data sources, and they graph it in their graphs, and they can see it. But they rarely have a need to query and process those pieces of data together as one cohesive unit. So I thought, okay, well, that's not very interesting, although I will show that later. And then maybe federation. But again, I came back to this situation where I think most people show it in Grafana. So I went back to the drawing board and I thought, okay, what can I say or what can I do that would be interesting for this crowd? And I went to the Prometheus repo and I thought, okay, I'll look at issues. I'll see what people are asking for. I didn't want to look at bugs. I wanted to look at like feature requests, right? So specifically, I wanted to look at what people were asking for in PromQL and what was labeled as an enhancement, right? What are the things that people want to get out of the query language that they can't currently do? I know that people love PromQL, but my assumption was it is not the answer to every problem you could ever possibly have. So I uncovered a couple of interesting items. So there's this one, subquery for range selection. So this is like a subquery thing. And this was like a long issue. It's still open. It was opened a couple of years ago. And there was like a discussion on a Google group that was linked in there. And this is like somebody asking, hey, I want to do something like this, right? And this shows kind of what they want to do. They want to calculate the rate in 2-second intervals over the last 60 seconds, which would be 30 data points. And then they want to get the minimum value of those. Ultimately, this is basically subqueries is what they're asking for. They want to do some query, and then they want to wrap that with some other query that processes that result, right? So here towards the end of the issue, we have Brian saying, don't hold your breath on this one. I'm going to flag it as maybe, and also not as easy as it looks, which I agree with on the latter part for sure. Ultimately, the answer to anything that is related to subqueries, it seems, is recording rules, right? So you configure a recording rule to calculate those rates, and then you can do a PromQL query against that resulting series. The problem with recording rules is it doesn't do anything for you in terms of ad hoc exploration, right? You need to know ahead of time what questions you're going to ask, which kind of sucks. All right, we'll come back to this one. Don't worry. So here's a request for covariance and correlation features. And again, you have Brian coming in and saying, well, that's like heavy statistical analysis. That's the kind of thing that you want to do in R or Python. So really, do it there. And I bring these things up not because I want to malign Brian and the other Prometheus developers. I actually think they do a really good job. And the truth is, with Prometheus, I think that its focus, this pure focus on metrics and solving this metrics monitoring problem, is actually a key strength of the project. And ultimately, like myself being an open source person as well, I think saying no is an asset. Projects are as much defined by what the maintainers say yes to as what they say, or as what they're defined by what they say no to as what they say yes to. So, but ultimately there's still this problem of there are query workloads that people want to do with their Prometheus data. There was this talk from last year about doing data science-y kind of stuff with Prometheus. And basically the talk was, query your data out of Prometheus and then work with it in R or Python. So I thought, okay, there's an idea here. There's something that Prometheus users want to do that maybe we can help out with the new language. So let's liberate the data silo. Let's pull the data out of Prometheus and make it so that we can process it in other interesting ways that maybe don't exist in the database itself. So enter Flux. This is where I think actually the more interesting pieces of our new language plus Prometheus kind of reside. So let me get into the language elements. We're going to go through like a whirlwind introduction of it. So here's what a query looks like. This is querying from InfluxDB, the Telegraph database. We're looking at the last hour worth of data, and then we're filtering it down by these tag keys. Underscore measurement is basically our version of metric. Field is not something that exists in Prometheus, but underscore field is basically a special thing in Influx for how you would work with Influx data in Flux. As you can see, there are comments in the language. There are functions, these different things. There's this crazy looking pipe forward operator thing, which if you've worked with Elixir, you've seen. I've also seen people propose this for JavaScript. I don't know whether or not that's ever actually going to happen. But basically the idea is that you take the output from one function and send it to the other function. So we're piping the data or the output from a function forward to the other function. We've named arguments. Flux as a language does not support positional arguments, and that is by design. I like named arguments because as a newbie coming into the language, I don't need to know what the parameter specification is for a function to know what's being passed in or know what's being done. I think it's a bit more readable for novices. It's maybe a bit more verbose for people who are creating queries, but you read far more code than you write. So let's optimize for the common path. There are string literals. There are duration literals. This is like a relative time here. We can also have time literals. Actually, I put those in quotes. Time literals do not need to be quoted. There are anonymous functions. That syntax looks similar to stuff you'd see in JavaScript. And ultimately, the language as a whole looks very, very similar to JavaScript if you've done a lot of work with it. There are a bunch of different operators. There are a bunch of different types that the language supports. The ones on the left, standard types. Some of the ones on the right, I think, start to get more interesting. Object function, namespace, table, and more importantly, this idea of a table stream is a first-class citizen within the language. So there are different ways to run Flux as a language. There's the interpreter, which I'll be showing primarily in most of my examples here, which is basically like Python or Ruby or whatever. It's basically just a runtime where you can run a script from your laptop or from a server. There's an API server, which has an HTTP API. It's basically a stateless application server that can query whatever data source, combine the results together, do the query, and send the end result back to the API caller. And in the future, the next release of InfluxDB, we will have Flux as a supported thing. And also it will be in the 2.0 alpha, both of which we hopefully will be releasing next month. There is a user interface currently in the works in Chronograph, which is our UI for the stack. It's basically a builder where you have a code editing screen, but the idea is also you'll be able to build a query without knowing the language at all. You won't have to know the language to create that. We've partnered with the Grafana Labs folks because we want Flux to have first-class support in Grafana, and they've started a builder there as well. All of this stuff is very super early. It's very it's basically pre-alpha, but we're trying to get all the pieces together so we can start to get feedback from the community. So why is Flux? Why do we need another language? Ultimately, I think Flux is interesting because it's all about data. The thing that we're trying to do is we're trying to work with data and do transformations on it and do analytics on it and do all sorts of other stuff. So let's pull this back to Prometheus. Let's look at time series data from Prometheus. Now, I don't do live demos because live demos freak me out. But just to show you, my live demos are actually slides, basically. But to show you that I'm not completely lying, here. Yeah, so there's my node exporter. There's my Prometheus server running. And then over here, I'm not even going to type it out. I'm just going to go back up. All right. So I have the Flux interpreter. I'm telling it to execute the script that I'm just handing in on the command line. I have the from prom function, and I'm just actually passing in a raw Prometheus query. And then I'm saying I want only the last minute worth of data. Execute that, and there's not enough real estate here to show it, but there are results, I promise. All right, we're gonna switch back over to slides now. Okay, so basically here it is kind of scoped where you can see the results on one screen. The actual results aren't important, but what you can see there is you have a table of results. And here we have the actual query that we had before. In this case, we're actually saying, get us node CPU seconds total and match to the 0 CPU and the idle mode, and then look at the last minute worth of data. So that's what this query looks like in a bigger font with nicer stuff. But going back here, we can see that we return a table of results, and the table has these keys: name, CPU, host, instance, job, mode, start, and stop. These keys basically serve as an identity for the table. Actually, the value of these keys serve as an identity for the table. If you look at their values below, they're actually all the same. So there those are, right? But we also have the actual time series samples themselves, which are stored in special columns called _value, which is a float, and _time, which is a time. So now I just want to show, let's limit what gets shown on screen, because some of those columns I don't really care about. So we're going to pipe it into this function called keep, where I specify here are the columns I want to keep in the result and send those back. And there we can see here, we've got less noise there in the result. All right. Here's what multiple time series in Prometheus looks like. So we're going to use this query here, where we're going to do the seconds total again, the 0 CPU, but this time we're going to look for either idle or user as the mode, and we're going to keep the same columns. And in the result set, what we can see is we have two separate tables. And that's a key thing in this whole thing, which is each time series gets split out as separate tables. So here you can see the keys there are the identifiers for the table. And if you look at mode, there's one table for user, one table for idle. And then here we have the actual samples themselves. Tables are basically the base unit that we're working with as we work with data in Flux. And the nice thing about this abstraction is that it's not tied to a specific data model or schema or anything like that. It's not tied to, say, InfluxDB's idea of a measurement and tags and a field, or Prometheus's metric and labels, or whatever. Like SQL databases, it actually maps perfectly with, because they're all tables. All right. So let me talk, before I get into more of that and how we actually transform the data, I wanted to talk a little bit about the filter function. So before, what I was doing is I was handing in a raw query into Prometheus to have it process that. That's not ideal. Like what I'd actually rather do is compose my entire query in Flux and have the engine just intelligently translate whatever it can down to Prometheus, and then whatever it can't, do post-processing once it gets the result. So here we have the filter function. We're saying match this name, match this mode, and match this CPU. And there we see there's the actual filter function that we're using. And importantly, down below, we can see the Prometheus query that actually sends to the Prometheus server. And also, what the range does is that sets the start and end time that it's sending to Prometheus as the query. So I also wanted to show this one because I think it's a little weird. But in Flux, you have like an in match. So if you see in the filter function, we're saying r.mode in, and then we pass it an array of idle or user. And what that does in Prometheus is it translates that into this kind of like regex matching thing, which is, I think, a pretty ghetto hack. But I don't think you can do ORs. Ultimately, if the cardinality of whatever it is you're regex matching against is high, this is going to end sadly for you. All right. So let me talk about some aggregate functions and how they work within this like table space. Right? So here we're grabbing, again, name, mode, idle, either from the 0 or the 1 CPU, and we're grabbing the count of those things. So as we would expect, there are two separate tables, one for the 0 CPU, one for the 1 CPU, and then we're seeing the count, which is 4 samples. The other thing to note is that the time is the same as the end time for the query. So basically what the aggregate does is it'll compute that aggregate, but an aggregate doesn't make sense in terms of the timestamp for a single sample. So what it does is it sets the timestamp by default to whatever the end is of the range, but you can actually configure that to tell it what timestamp you'd want to use. So, and again, like you have this idea of the keys that define the table. Notice the stop is part of the definition. The table's identity is the table that has those specific keys for name, CPU, and mode, but also this specific stop time. And there's everything all in one place again. So in the language, we have within the tables that we send around, we have this concept of an underscore start and underscore stop like columns. Anything with an underscore is basically like a system level column. And those columns are basically about windowing data in terms of time. Basically like slicing and dicing the different tables into different components of time. So I wanted to dig into what the window looks like. So basically we have this query here, right, where we're just grabbing the last minute worth of data. And there we can see we pull back one table. And you can see that the start and stop time is based on the range of the query, right? So the range is the last minute, and the start and stop time are a minute apart based on when the query was executed. So now we're going to call the window function, and we're going to say window it to every 20 seconds. So every 20 seconds, I want to create a window marker. And actually what you can conceptually think of this as is taking that one table and splitting it into tables where you have 20 seconds worth of data for each one of those, right? So it's all the same samples still, but now they're split across 4 separate tables. And then we can send an aggregate function at it. And when you send that to an aggregate function, it will compute that for every table that you have in the stream. So then we can see, okay, now the tables have all been reduced to a single record, where the record is the actual aggregate result. And then finally, we can unwind those tables. This looks kind of weird. We're probably going to change the syntax a bit. But we can unwind those tables and roll them back into a single table of results by calling window and saying the every boundary is infinity. We don't care. Basically, combine them all together again. And this would work. So with the query that I had, the initial table that I had was one table. But say we had pulled back 2 separate time series worth of data, this works across multiple different time series. So if I had pulled back idle as one and mode as another, what I would get back after all of this is I'd get 2 tables, one with the idle aggregates, one with the mode aggregates. So basically what window does is it converts n tables into m tables based on time boundaries, right? Like that could be fewer tables, more tables, and by default, underscore start, underscore stop, and underscore time are the ones that get used. So let me cover group really quick, and then I'm just gonna blaze right through. I think I have like 5 minutes, and I'll still have 5 minutes of questions. 4. Okay, so group is the other piece of this, which is it converts n tables to m tables based on values, right? So say we have this here again, CPU 0 or 1, idle. We have 2 tables there like we'd expect. And now we want to group it based on the name and the mode. So we want to combine those tables together. So what we get is a single table of results with both the 0 and the 1 CPU in a single table. Now say we want to, now if you look at that, they're arranged in basically, it's like a union. They just unioned them together. So now say we want to actually sort those by time. So now they're sorted by time, and you can see they're all interleaved. Okay, so let's get back to this subquery support for range selection. This is gonna be really fast. This is what that query looks like. This actually works. So I'm querying from Prometheus. Here I'm actually showing that I can pass in the host. By default, it queries the local host, but it can be any Prometheus host anywhere. I'm doing the filtering, so I'm looking at node disk written bytes total. I'm doing the range. I'm transforming using a non-negative derivative. I'm breaking those results out into 10-minute windows. I'm getting the max on each 10-minute window, grouping it all back together. And then finally, just for fun, I decided to show mapping over the records in the table to do some sort of transformation on them. Right, so I'm converting it into kilobytes. Here's an example of querying from multiple Prometheus servers. So I have data center 1, data center 2. I construct a query for those, and then I call union to cross the streams. And then I can compute a sum or some aggregates on that. So with Flux, you can actually work with data from, you will be able to work with data from many sources. Influx itself, Prometheus, MySQL, CSV, S3, and the idea is you'll be able to combine those results at query time to do things that you weren't previously able to do, at least not that easily. You can define functions in the language, so this weird pattern where we have window, then an aggregate, then another window to unwindow the results, that would be very, very common. So you could just say, let's define a function called window aggregate. We'll take a function, and this last thing at the end is basically that stream thing that says like this function is pipe forwardable, and if you pipe forward something into it, it will get assigned to this stream variable, which then you can reference in the function, right? So we call stream pipe forward to window, pipe forward to the function, pipe forward to window, and we have the result. There are also going to be packages and namespaces. We don't have this yet, and we're still kind of like narrowing in on how exactly we want this to work, but this is an example of how maybe it could. So we have Flux helpers. We define the function, and then in a separate script, I could import it, and then I can call that function. And the idea is we want people to be able to share code easily. So project status, everything in this talk is a prototype. There is some working code. It's all on a branch, which I will tell you about in a second. The end of this month, we want to have a proposed final spec for the language. There is a spec that's publicly viewable now. Next month, we want to release these things as basically alphas so that people can play around with it. We want to iterate with the community. And then finally, we want to do optimizations. We've done no optimization on this yet, so there's going to be a lot of room for that. There are a few avenues of future work that I think are particularly interesting for working with the Prometheus crowd. One is, right now, the way a Flux query like compiles down into Prometheus is pretty basic. So we could have more complex compilations into PromQL. We also have been thinking about adding a PromQL parser for the Flux engine. So basically parse a PromQL query. Flux, the idea of the language, is decoupled from the actual engine itself. What the engine gets is basically a DAG that's represented as JSON. So if we can parse the PromQL language into that DAG, then it could execute it. We could potentially add Flux into Prometheus. I doubt this would happen, or would it be accepted? I don't blame you. But here's actually the most important one that I think is the most interesting, is adding an Arrow API for Prometheus. 20 seconds. So Apache Arrow, for those of you who don't know, it's a cross-language development platform for in-memory data. It specifies a standardized language-independent columnar memory format for flat and hierarchical data. It's for analytics, friends. So the idea here is that we could add an API to Prometheus where you could stream data out of it, but stream it as Arrow buffer data. So it would support not the entirety of PromQL, but only the minimum amount of stuff that it could do, where you could guarantee that everything could be sent as a stream. So anything that you would send to it would have no risk of basically ooming the Prometheus server or anything like that. And with Influx, that's actually how we're building InfluxDB plus the Flux engine, is we're decoupling the idea of that pure storage from the actual engine itself. All right, these can come in later. Yeah, there were more. I thought I had 30 minutes. I'm at 26:30. Yes, so thank you. Questions?
So we have roughly 3 minutes for questions.
Okay. Thank you. So we have performance analysts who have approached me because in the past they were able to make use of data from, say, Graphite and kind of wrangle it in spreadsheets from a sort of business perspective. And I've been wondering how, between this and Thanos, like what would be the best way to kind of meet that use case?
Making data available to data scientists so they could work with it in spreadsheets.
Yeah.
I mean, we would add, so I guess if the Thanos people could probably talk about it, but one thing I was thinking about is this here, which is basically Flux has this idea of inputs and also outputs. So the idea is you could do from prom, do some data, and then you could write it to a CSV file or to Feather. Feather is basically the on-disk format for Arrow, and R and Python actually work really cleanly with either CSV or Feather formats. Feather is much, much faster because it's a zero copy kind of thing. But yeah, the idea is they could run this at the command line and then have the data to work with in a format that works for them.
So again, I'm learning. So for Flux, it's for data scientists in analytics, correct?
Kind of. It's for all the people. All the people who want to do things with data.
Thank you. So is there any possibility of, I guess, using with Grafana, like putting like a UI in front of this for visualizations?
Yeah, so they've already started the work. David, who is here somewhere hiding, hey, just right there. You can talk to him about that because he built it.
Awesome. I was just curious about that.
Yeah. We want Flux to be supported in Grafana, in our user interface. And I mean, the reason why we MIT licensed it is we want it to be supported and used as widely as possible, whether or not people are working with Influx, right? So like Telegraph is, I think, our most successful open source project. And the reason it's so successful is there's no requirement that you run Influx at all if you want to use Telegraph. And we want Flux to be the same way.
Kind of following up on that, do you see the Arrow API being something you can implement for other databases? So maybe you want to combine data with Influx from Hadoop or somewhere else, and instead of having, from S3, you have this kind of from Arrow?
Yeah. Yes, I do. And actually, I think future databases will be based on Arrow. And the thing is, like, the big data platforms already have a lot of support built in for Arrow. So if you want to work with Arrow, like in Spark or anything like that, it's already kind of first class. Like Wes did a bunch of work while he was, Wes McKinney, the guy who created, one of the creators of Arrow, did a bunch of work while he was at Cloudera to basically try to integrate those systems. And the idea is it's a format that's cross-language, cross-platform, so you can get zero copy semantics for these things and work with whatever tool you want to work with, but do efficient analytical processing.
Hi there, I'm over here, behind the beam. So the language that you presented over here is, I think it's something called concatenative programming, right? Where you keep on smacking stuff at the end of a script to map data through it. Do you by any chance know how it relates to some of the other languages in that field? I'm not an expert on concatenative programming.
That is the first time I've heard that phrase, so I would have to be educated on that. Yeah, I mean, the thing is, you don't necessarily have to just tack something onto the end, but I do think because it's kind of like flow-based and functional, it does lend itself nicely to building up a query over time. Like, in theory, you could do the same thing in Lisp, but instead of tacking it onto the end, you'd be wrapping it, right? Like, and there is actually a way to call to show Flux, to call these functions and make it look like Lisp. Although I don't know why you'd want to do that. You could.
Okay, thank you very much.
Thanks, everyone.